Alright, it's recording now. I sent an announcement last late afternoon yesterday, and it was just to remind you that you had stuff due this morning, the notes for the Unit 2 videos, but also I had posted the practice problems for the Unit 2 videos. They should be fairly straightforward. I call a couple of them more challenging. If you use your notes or if you use a textbook, I'm sure most of you can get through these four problems. And I'm going to go over these four problems, or at least some of them, today. What else was in the announcement? Those of you who are taking the lab have stuff due tomorrow afternoon. Announcement number 5, as you see on Moodle, are office hours. Jose has one at 1 o'clock, and he'll be available Sunday for last minute review. Mine are today at 4, and Saturday and Sunday, both days at 11 a.m. to 12, and I'll be able to meet people Saturday night and Sunday night if you come across any difficulties. Yeah. In terms of the rest of Moodle, it's listed in chronological order. Just make sure that you see what is due. I don't put it on Moodle, I don't think, but I do accept late assignments. Typically, I think, oh, for this one, if you haven't turned in your notes yet, I can accept them up till 5 o'clock. Okay. Usually it's the window closes between 10 and 24 hours after the due date. Try not to have too many things late, because yeah, you don't want to fall behind. I am recording this lecture. Wednesday's recording is under Wednesday's section along with the class notes. I'll try to do the same thing, post the class notes and the recording link on Friday. Alright, so like I said, we are going to go over, just double check, we're going to go over some of the Unit 2 problems. Let me get back to my document camera. Screen. Here we are. Hopefully you can see my screen. I'm trying to maximize it as much as possible without having anything blocked off. These were the four problems that I mentioned on the announcements. I don't know if we'll get through all of them. These are the practice problems, or we call them after video assessments. The idea is after you watch the videos and take notes, you could do a self-assessment and see if you understood the concepts by doing some of these problems. And the first one, page 1, number 2, it's not necessarily hard. It's just that it's something that a lot of people are not very used to, and it has to do with resonance and the resonance of molecules that have a carbonyl group. So that's what I'm going to do first. Before I get to that, after we do some or all of these problems, I'm going to introduce Unit 3. Unit 3 is relatively short. I imagine that eventually there's only going to be 3 videos. Okay, and so there's no videos yet. But I do understand that a lot of you want to get started on it as soon as possible. So I will give myself to the end of today. So only videos posted by 4. Because at 4 p.m. I'll have my office hours, so I want to get done by 4 today. The only videos posted by 4 today will be on the exam. I think that's it. I still have to check your extra credit. If we're running short of the 12 points that I want to give for extra credit, then I'll figure out something between now and 4 to get you those other points. So there are at least 12 extra credit points available. Let us, if there are no problems or questions, let me double check the participants list. Okay. First one is page 1, number 2. We'll call this, oh man, how are we going to label this? Unit 2. This is video 02A50, and this is 2. Okay. It says to draw resonance, but really what you're doing is drawing mechanism arrows to get to the other resonance structures. Now, the idea is if you have more than 2 resonance structures, for instance, if you have A, B, and C, your mechanism arrows have to go from A to B and then B to C. I know for some of these it's tempting to go from A to B and then go back to A and do A to C. But you should learn how to go from one contributor to the other without having to backtrack. And I think we'll have an example of this one right here. But let's do the first one. The first one is kind of tricky because you don't normally think that there's a resonance structure for this molecule. First, it's neutral, okay? And also, well, you only have one pi bond. Normally with resonance, the molecule is charged, or you have multiple pi bonds. But there is a real resonance that occurs for this molecule, for any carbonyl group, actually. And that resonance is pushing the electrons up to the oxygen. And this, like I said, this is real, but it's minor, but it's still a resonance structure. And what you get is separation of charge. And, that was one of the things that when we talked about picking the major contributor, you don't want to pick the one that has the separation of charge. Okay? Even though this is minor, it still exists. I did say that all of them have at least one other resonance contributor. So I would count this as the correct answer. Now, that brings up an interesting point for the next one, because let me show you this one. It's really a stylistic preference. So this is the anion that I see on the problem sheet. Because of this resonance, yes, I would have to count as correct if you did the same thing for each of these carbonyl groups. Okay, not at the same time, but separately, right? You don't want to move, you don't necessarily draw mechanism errors that are kind of disconnected from each other. Okay? But if you have an anion like this, my preference is that you use the anion to get to the other resonance structures. Not only that, I don't necessarily want to create a molecule that has 3 charges. So you can imagine, okay, don't draw this, but you can imagine if I drew this, okay, your result would be a negative charge on oxygen, a positive charge on carbon, and a negative charge on this carbon right here. That, in my mind, is too many charges. Now, there are molecules that have 3 formal charges, but those are very rare. My point is, we're working on a unit that has many, many carbonyl groups. And when you have an opportunity to draw other resonance structures besides this one, my preference would be you do that. Don't draw this resonance. Now, if you do, it will be counted as correct, but you got to get all the other ones as well. So my first resonance structure that I want to draw is a result of these two arrows. Okay. Remember the trick for resonance? If you have an anion, start with the atom that has the negative charge and move that lone pair. I chose to move it to the right. Half of you would probably choose it to move it to the left. It doesn't matter because I am going to get that resonance structure on the left, that anion on the left in just a bit. Okay, so this is just one possible answer. Resonance, you have to practice a lot for it to click. That's a good resonance contributor. There's one charge. We were able to localize that charge. We got it onto a negative, electronegative atom, oxygen. So this is good. Now, how do we get to the negative oxygen on the left? Because again, what was to prevent me from putting this lone pair to the left and putting this pi bond onto the oxygen? Nothing's preventing me from doing that. Again, half the class on average would have moved it to the left. This is how we're going to do this. I'm going to go back, and instead of putting this pi bond onto the carbon, remember a pi bond can move its electrons to the adjacent atom or to the adjacent bond. So we are going to jump like that and push that pi bond up. So what we get is a structure that I would have predicted that half the class would have drawn first over here. So take a look at this. Okay, so that's the lone pair. So these are the three main contributing structures. Now, again, if you choose to go ahead and do the carbonyl resonance to get something that looks like this, that's correct, okay? I would count it as correct. But if you only have these three, this will get full credit. Okay? All right. Is there any other else? Any other resonance structures I could draw that only have one charge? I don't think so. So again, remember how I was saying that you have to go from A to B to C? What if, and then I'll drop it. I know I've been repeating myself. What if someone draws this structure, go to this structure? So now this is B. You should be able to get to C by moving those electrons all the way across the molecule. So the order doesn't matter as long as you get to each contributor in a rational way. And let me actually put that as an emphasis. A, B. Let's take a look at this. We have another anion. What am I trying to test you with this molecule? Test you on with this molecule. Okay. So first of all, there's a negative charge. I have to give you that, but I don't have to give you the lone pairs because you have, well, experience, but you also have rules to determine how many lone pairs that oxygen has. You want to fit the octet rule, so there should be 3 lone pairs. My suggestion in the problem was to draw all the lone pairs because the trick is if you have an anion, start there. Start with a lone pair for the anion and move it to the adjacent bond. Okay? Now, you can imagine that if you made a double bond right here, this carbon right there has 5 bonds. But the good news is we could resolve that. And we could resolve it by pushing the pi bond to this carbon right here. Now, what's the purpose of this molecule when I ask you to draw resonance? I'm trying to see whether you can resist the temptation to do anything with this double bond. There's no way that this double bond can participate in resonance because it's too far. Take a look at this anion now. If I move it to the left, this carbon will have 5 bonds, and there's nothing we could do about it. If I move to the right, what's going to happen is I'm going to get back this original structure. Now again, if you choose to draw a resonance that looks like this, with the negative oxygen, positive carbocation right here, I'm not going to take off points for that. Okay, I'm not going to take off points for that. It's just that we have two structures that are much, much better, much, much more contributing than the one where we're going to have a carbocation and anion. Okay? Uh, I guess what I could say is that when you have no other choice, do this resonance. If there's nothing else you can do this resonance right here. So we have a neutral molecule example. We have an anion that could go either way, left or right. We have another anion where I'm trying to tempt you into using this double bond here, but you can't. It's whatever arrow I draw, it's going to be unreasonable. I'm going to have a carbon that has 5 bonds, most likely. Where's our cation example? So there's a cation example right there. Let me draw that for you. It's as if we had this aldehyde and we protonated it. Now, why is this resonance, the resonance of this protonated carbonyl, important? Because for your acetal reactions, for your hemiacetal reactions, in the mechanism, the alcohol is not a good nucleophile. So we have to make the electrophile even more attractive. And how do we make it more attractive? By protonating the oxygen. Because probably the first resonance that most people would draw is this one right here. So what happened? We get a plus charge right there, and we have the rest of the molecule. You see why protonating the carbonyl makes it more reactive? Because it actually has a pretty good resonance that puts a lot of the charge on the carbon. That's where the nucleophile attacks, right? This almost looks like the beginnings of the hemiacetal formation, where you could have a methanol or another alcohol be more attracted to this carbon because it has a bigger partial positive charge. Now, when we draw the mechanism, right, we attack this carbon right here, the one that has a protonation on the oxygen. Okay, but we attack this carbon because in real life, it's really a combination of these two, and this carbon is more electropositive than if there was no protonation here. Okay? I believe I talked about that in the last video for Unit 2. I hope I did. Let me double check. So here are my notes for Unit 2. And the last video, I'm really hoping I talked about activation. Okay? If you don't understand the reason why it's good to protonate, if you want to attack this carbon, the explanation is on the last page or on the last video, the last thing I said on that video, which was activating the carbonyl group for attack. Now, why didn't we protonate in other reactions, like for instance reaction B? We didn't have to protonate for reaction B because reaction B had cyanide. Cyanide is a very good nucleophile. So the attack happens pretty readily. But I can tell you now that if we didn't have any acid here for this reaction F, that methanol is not going to really attack this carbon. Maybe it's very, very, very small percentage. Okay? By protonating that carbonyl, what are we able to do? We're able to have this resonance right here. Okay, so cover this up. Once you protonate an oxygen, you have this resonance contributor available, and that carbon is more partial positive. Do I want to see this in a mechanism? No, I don't want to see this in a mechanism. All this resonance tells you is that it supports the fact that protonating that oxygen makes it more electrophilic. So let me show you the acetal formation. Okay, so this was also in the video. Let me find it real quick. So here we talk about, here we talk about hemiacetals. Where's that mechanism? That mechanism is right here. There's the protonated carbonyl group. Do you see that I don't make the resonance structure? I go ahead and attack with the alcohol onto that carbon, and I'm almost close to the hemiacetal. The hemiacetal's right here. All right, so again, for the mechanism, don't draw the resonance. The resonance explains why this carbon is super attractive, because there is a resonance structure that has a plus charge on this carbon. Okay? Now, let's see. You might ask, well, don't we have that same idea here? Yeah, we have the same idea here without protonation, but that plus charge is not as strong as if we had protonated. And I tried to explain that right here. This versus this. No protonation versus protonation. We do get the resonance, but I can tell you now that this is a more major contributor than this resonance here. Okay? I don't want to belabor that point, but so there's the carbocation. But look, we have a double bond right next door. You know, if we had this from Organic Chemistry 1, you would know what to do, correct? You would push this pi bond next door, and we get a third resonance structure. Okay, so I'm missing something. That carbon's naked. The carbon has 4 bonds now, but when I move this pi bond away, the carbon only has 3 bonds, so your plus charge is there. Again, we have an ABC situation. Is it possible that I might get one student go from A to C? You can go from A to C, because for A, if you move this pi bond next door, yeah, you will get C, but then you gotta go back to get product B, to get contributor B, by moving this pi bond to the left again. I just like doing this systematically, stepwise. If I could get a new resonance structure by only drawing one arrow, I'd rather do that. I'd rather do that. Okay. All right. So that is page 1, number 2. That was quite a bit, but I want to make sure that there's no confusion about what I need when I talk about resonance. Also, what I need when I talk about mechanism arrows, everything in green. Every green arrow started from a bond, or every green arrow started from a lone pair. You will be marked off if your green arrow starts from a charge. Okay, so that green arrow cannot start from the charge. Okay, you have to literally draw out the lone pairs and draw it from a source of electrons. It will be wrong if you draw an arrow from an atom. Okay, we don't have any potential examples here, but like a proton transfer, it's not the H that's moving, it's the base that is grabbing. Okay? If you recall from Organic Chemistry 1. But again, this will be posted. You can take a screenshot if you want, but this will be posted right after the lecture. Okay? That, to me, looks like a good answer key, number 2. All right. If there are no questions yet, I don't see any hands. Let me go a little bit faster, and we're going to look at the second problem. Too long. Page 3, number 3. Page 3, number 3. What is that all about? Okay. I gave you a clue that it's acetal formation, but you knew that because we have a carbon that's connected to an OR group, connected to an OR group. If I ask you to hydrolyze this acetal, I think many of you would be able to make your cuts, dotted lines, separate or spread out the molecule a little bit, but you would realize that everything is still connected via these carbons here to this middle carbon. The middle carbon, the one with the dot, yeah, I'll do that. The one with the dot, okay, has a carbonyl group. Acetal formation is 7 steps. Hydrolysis of an acetal is reverse, so it's still 7 steps, just in the opposite direction. I said this was something that I'd want us to know how to do, so we're going to do this. Number 3. Okay. If you want, this is still Unit 2. Try to keep everything labeled. It will help. Whoops. Try to keep everything labeled. It will help you study. Okay. From the video, you could probably guess that you will get a mechanism, likely acetal formation or hemiacetal formation or hydrolysis. Um, Hydrolysis is actually a different video. Okay. This is video number 02E20. I gave you the starter material. The other way that you could learn or memorize mechanisms is to verbalize. I would not get a false sense of security just because you have open notes. Even if you had open notes, if you didn't practice, you might be very intimidated by a problem that looks like this. Okay. So, in terms of formation, the acetal, I just went through a whole deal saying that hydroxyl groups, alcohols are not very good nucleophiles, and we have to protonate. Whenever you're with acid, most likely you go to protonate it. Think back about the epoxides. Where there's acid present, wasn't the first step to protonate the oxygen? Same thing here. See, proton transfers are pretty easy to do. They're fast. It's just a very simple transfer of a proton. If that helps you get closer to the product, then I would do that. Now, those of you who are literally imagining yourself in the round bottom flask, and you're imagining these molecules bumping into each other, colliding randomly, yeah, you might overthink things and you say, well, I could protonate this oxygen. Okay. Didn't we do a lot of that with the alcohols? Didn't we protonate the OH to make it a good leaving group? True. But when you protonate this oxygen, actually nothing else will happen. There's no there's no base to take it out, really. When you do a mechanism, yeah, infinite number of things can happen. But you got to draw the pathway that gets you to the product. So you can imagine the proton bouncing back and forth between this oxygen. Nothing really productive is happening. But when you hit this oxygen, that carbon becomes a very good electrophile, and then we get an attack. So that's your thinking. Okay, those of you who are on top of things, you don't want to overthink things. Okay. Now, this is interesting. I did say, I do continue to say that there's a little bit of water when you have sulfuric acid. There's no such thing as pure sulfuric acid. So my debate is whether I want to use sulfuric acid or I want to use water. I'm just going to keep consistent. I'm going to use protonated water, the hydronium, and I'm going to protonate this oxygen, make it a good electrophile. This is the first step. Whether you use equilibrium or not, it doesn't matter to me. When that carbonyl gets protonated, the reaction is going to go like a shot. Because that carbon is very electrophilic. It's very partial positive, and we're going to get our first addition of our alkoxy group. Remember, what are we aiming for? We're aiming for 7 steps. Memorize the first step. Hopefully when you see this product, a cascade will happen in your brain. And you said, well, really, the only thing that's productive that could happen is this attack. What's the hard part here now? The hard part here is drawing the molecule. Put your dot. Whenever I cyclize something, we didn't have a lot of experience in Organic Chemistry 1 with this, but whenever I cyclize something, figure out how big that ring is. The ring is 1, 2, 3, 4, 5 atoms. 1, 2, 3, 4, 5. See, I'm not making the ring with this oxygen. This oxygen is looping around and we have 5. All right? Dot. Okay, one of your atoms on the ring is that dot. That oxygen connects to the dot. So we have this oxygen. 1, 2, 3, 4. Up. 1, 2, 3, 4. Start over. It's a little bit of practice. 1, 2, 3, 4, 5. Okay. You could always add and decorate your ring later. Try to get the right number of atoms on the ring first. So what happened to this oxygen? That oxygen is still on the dot. And now there's an H. Right? That's a single bond now. What else is on that dot? That dot has 1, 2, 3 carbons and then the hydroxyl group. 1, 2, 3, and then the hydroxyl group. So we're close. We're close to hemiacetal. What do we have to do next? We have several options. Oh, shoot. Oh, no. Did anyone catch that? Okay. Did anyone catch that? I forgot the hydrogen here. Okay. Okay. Also in the first step, we've created water. I'm going to use that water actually to remove this hydrogen. If you look this up, I don't know, Khan Academy, other websites, they're going to take shortcuts that aren't really true. The shortcut is to protonate what? To protonate one of these oxygens by deprotonating this in the same step. You don't want to do that. You want to do this stepwise. Okay. So here we have this. Okay, everything's neutral. What is our goal with this reaction, acetal formation? Remember, it's this oxygen that totally goes away as water, right? These two oxygens that are left behind in the product are actually the oxygens of the hydroxyl group. So our goal is to get rid of this OH, get rid of this oxygen that was originally the carbonyl. And, you could always put your dots to keep track. How do we get rid of this? We got to protonate it. Okay. So when we deprotonated this oxygen, we made an acid. Remember, we're hoping for 7 steps. Right now, it's not worth worrying about the number of steps just yet. We do have the hemiacetal, right? So that hemiacetal was accomplished on the video in 3 steps, right? 1, 2, 3. So we're on track there. And yeah, we created water. This is step 5. Step 5. Step 5 was the weird step. Step 5 was the step where we used the internal lone pair to kick out water. Because I know it's very tempting. It's very tempting to use this hydroxyl to come in and kill 2 birds with 1 stone. But in real life, that water doesn't leave because of this oxygen. It leaves because of this lone pair. We're almost home. What happened here? Double bond. Again, plus water. So far on the screen, 1, 2, 3, 4, 5 steps. But you see what happens next? this. Okay. Again, what is the trick? The trick is know how many atoms are in the ring. We're definitely cyclizing. 1, 2, 3, 4, 5. Start with the dot, that oxygen attack. Then you have 3 other carbons. So it's just 1, 2, 3, attach. That double bond is now a single bond. Okay, so we have this. 1, 2, 3, attach. And don't forget that hydrogen. Then we have to use water again, and we are done. So it looks a little bit different because I twisted the molecule and the oxygens are on separate sides, but it doesn't matter. It's the same molecule as this one right here. Actually, if you make a model of this, you could orient that molecule so it looks like this from your point of view, but from another person's point of view, it would look like this actually. It's tetrahedral. So it's symmetrical actually. It's a full mechanism it's a full mechanism 7 steps. You have 1, 2, 3. I started to lose my equilibrium errors. 4, 5, 6, 7. What's even harder, in my estimation, is to go backwards. How do you take this and hydrolyze it back to the starting material? The strategy there is that if you have this, ask yourself, the last step was deprotonation. Deprotonation. So when you go backwards, the first step should be protonation. Over here, step 5 was lose water. So I betcha for the third step going backwards, it's to add water. All right. So that is the mechanism for acetal formation. All right. Yeah, I do want to introduce Unit 3. So let me see what page 4 is. Page 4 is problems 2 and 3. Yes. This is page 4, number 2 and 3. How come I don't have Oh, page 5 is just allowed to fill in the products. That is the minimum that you would have to know how to do. But 2 and 3 are a little more challenging. We're only going to do one of them. Okay, so we're just going to draw the products. The mechanism is what? It's the reverse. This is hydrolysis. Okay. Let me show you this. Let's use our tricks. So this is, again, Unit 2. Number O2F20. O2F20. And we're doing just the product for number 2. Okay. I'm not going to do the mechanism. It's a little bit lengthy. It's 7 steps again. But let me show you the shortcut. How do I know this is hydrolysis? I literally put water and acid. Lyse, cut. Hydro means hydrate, water. So you're going to cut with water. You could identify that this is an acetal because there's a carbon right here that's connected to an OR group and another OR group. It just happens to be cyclic, no big deal. Cut, lysis. Draw your dotted lines. That's where you're going to take your scissors and cut. Okay. You're adding water. You're adding an H, an H, and an oxygen. So in the next minute, You can test yourself. See if you can draw me the product or products. I don't know. I don't know if there's one product or two products, or we cut this twice. Maybe there's three products. But see if you could draw the result of these cuts, and you're adding an H and an H and an O. Okay. This is directly from the video, this technique. Right, so take a minute for that. This is weird because I don't think there are a lot of examples where the diol is on a benzene ring. And what do I have as the other product? So here's your dot right there. Okay. If you watch the video, I talked a little bit about protecting groups. And what you're used to actually, it might be something like looks like this, right? You have two hydroxyl groups and two carbons, and you protect the carbonyl group. This is actually really slick. The way that I taught it is that we protect, let's say we're going in the reverse direction. We protect the carbonyl group via cyclic acetal. But what if we think about it the reverse way? What if we think about protecting the hydroxyl groups with this acetone? It's the same thing. One is protecting the other to make that molecule unreactive at those locations. For the most part, you're going to think of this as protecting the carbonyl group, okay, the cyclic acetal. We're going to have to do that in this synthesis. Okay? We're going to have to protect this carbonyl group. But do you know why we have to protect this carbonyl group? Let me show you that. This is an example that is not in the video. I did talk about protecting groups, but I think on the video I protected one over the other because, I wanted to do an addition to a ketone rather than the aldehyde. Let me show you that real quick to remind yourself. So if you took notes, like these notes I would have during the exam, okay, just in case. You shouldn't have to refer to them often. If you do, you're going to run out of time. If you do refer to them often, that means that you didn't study enough also. But look at this, acetals are protecting groups. Why did I use a protecting group for this synthesis right here? Because if I try to use a carbon anion to attack this molecule, it doesn't know which one to attack. I really want to attack the one on the left to get this product and leave the one on the right untouched. But the chemical doesn't know that. And actually cyanide, or not cyanide, but the alkyl anion can attack each of these with relatively equal reactivities. And actually, it's more likely to attack this because it's sterically unhindered. That's not what I want. The beauty of protection is that I said that if you have a ketone and aldehyde, the protecting group will react with the aldehyde again because it's less hindered. Now, if this aldehyde wasn't there, then you would protect the ketone. So the protection in this scheme was necessary because this molecule could have attacked either the aldehyde or ketone. Okay. What's going on with this synthesis? In this synthesis, it seems like we want to oxidize this primary alcohol to make the carboxylic acid. But what do you know about oxidation? That aldehyde can be oxidized as well, right? We talked about this, I think, in the alcohol unit 1. Oh, shoot. If I try to do Jones oxidation, I will oxidize both functional groups. Okay? So I don't. I want to only oxidize the primary alcohol. So the strategy here is protect, do your oxidation, and then deprotect. If those words don't click, okay, you have some studying to do, because I just literally told you the strategy. I told you the strategy to go from this molecule, right, to this molecule. Aldehyde, nothing happens to it, but I oxidize the primary alcohol to the carboxylic acid. In terms of notes, we have a primary alcohol, we have an aldehyde. Seems like we want to do an oxidation, particularly Jones oxidation. Right, go from a primary alcohol to a carboxylic acid, but we want to leave this untouched. Don't touch this. Ultimately, don't touch this. We're gonna have to protect it, like put on I don't know, put on some a helmet, protect this, do your whatever you need to do on this molecule, and then take off the helmet, take off its protection. So we should put a protectant group here. All right, so here's the synthesis. We're going to protect this as a cyclic acetal, just like we did on the video. And the most popular protecting group for carbonyl is, this is called ethylene glycol. Uh, ethylene glycol, GLYCOL. You have to draw what it looks like protected. Okay. Does that look familiar? That 5-membered ring from the video. Do your oxidation. Not PCC, right? PCC will only get you to the aldehyde. We want to use Jones oxidation. My preferred reagent is K2Cr2O7, potassium chromate, H2SO4. I'll just put here as an aside. If you want to write as little as possible, uh, chromium trioxide. Okay, if you can remember that. Or literally chromic acid is H2CrO4. It's like H2SO4, but instead of sulfur, you have chromium. So that's how one of my students last semester told me how they remember that. H2SO4. Okay. Now again, those of you who are really good at incorporating this information from organic chemistry, you have a danger of overthinking things. Because what that means is that you know all the possible nucleophiles, all the possible electrophiles, all the possible pairing up that can happen here. You might be asking yourself, well, I thought that we could hydrolyze acetals using acid. Yes, but you hydrolyze acetals using acid with water. So there, in this case, there's a lot of water and very little acid. Acid is more like a catalyst. In Jones oxidation, you try to limit the amount of water. So you can do this oxidation without the danger of this protective group coming off. Okay? Again, you don't want to overthink things. It's a possibility, right? In real life, you may have this protective group come off in 2% of your product or 1% of your product, but not a lot of it. To really get this guy off, right, you need to do hydrolysis. It's not a great analogy, But for instance, if you have a patient, you want to treat, one symptom at a time or one disease at a time, right? You want to focus on certain parts of the body and at times ignore other parts of the body. Same thing with a molecule. You want to target what you want to convert or transform without changing stuff on the molecule that you have to keep. Now, yeah, we did lose the carbonyl group in the middle of the synthesis, but we're confident that we can get it back. In terms of notes, you don't have to put this when you draw the synthesis, but remember this is your protection step, and this is called deprotection. Alrighty, so that is all the problems. The only thing that we didn't do together, I don't want to do another mechanism, is this hydrolysis here. Okay. What is the first step in this hydrolysis? Protonation. Protonate this oxygen. Okay. All right, let me see if there are any questions. Okay. Let me introduce Unit 3, and why are we doing carbohydrates right after all of this alcohol and carbonyl stuff? If you think about Unit 1, Unit 1 was alcohols, and there were other classes of molecules. I think we had ethers and epoxylates. Unit 2, ketones and aldehydes. Unit 3, okay. I plan to put up 3 videos before 4 o'clock. That'll be my deadline. And those are the 3 videos that you would be responsible for carbohydrates. Carbohydrates is our first biomolecule. If you think about what you're going to be working with a lot, if you continue on with higher level biology, you'll be working with definitely carbohydrates. The next one is lipids, like cell membranes. Then you have proteins, and proteins are made via instructions given by DNA. So there are 4 biomolecules. This is our first. And carbohydrates are actually alcohols, polyalcohols, that terminate either as a ketone or aldehyde. Or maybe not, I shouldn't say terminate, but they're polyhydroxyl molecules that have a ketone or aldehyde. That's carbohydrates. So let me show you an example of a carbohydrate. The example that I want to do is glucose. Glucose looks like this. If you look up glucose on Google, most likely they'll have the aldehyde group, right? The aldehyde group as CHO. Draw a long line, and I'll show you how long, because you need 4 horizontal lines. Glucose has 6 carbons, and chemists and biologists typically draw glucose when it's in the linear form with the 6 carbons in a row. The very bottom carbon is the CH2OH. Okay. I'm going to fill in these bonds in just a bit. Let me just give you the name of this, D-glucose. Those of you who are familiar with supplements, or I don't know where else where you can see this D actually. But that D means right-handed, dextra-rotatory. Because we do have carbons here. Don't worry, on the video I'll tell you how exactly to figure out whether a carbohydrate is D. The other one, the opposite, is actually L. But don't worry about that. I said carbohydrates are polyhydroxyl molecules. We have one OH, but we need more. We're going to fill up the OHs from the bottom up on these 4 horizontal lines by right, right, left, right. Okay. If you forget, these are not methyl groups on glucose. These are all hydrogens. So if you forget to put the hydrogens, it will be incorrect. So on the other side of each hydroxyl group, put your H's. Okay. Some people memorize this. Okay. I know it's open notes, but when you get into genetics or microbiology, I think you can impress Schmeichel or what's her face, the other one, um, by memorizing where the hydroxyl groups are. So you could either memorize, Dr. Alford. So you could memorize right, right, left, right. Okay. That D, I said it was right-handed. So the other way you could do this is, I know this is recording, so I'm not going to really show it to you, but you give yourself the middle finger, okay, and then you go sideways. I'll show it. And you have this. Where your fingers are pointing, that's where your hydroxyl groups are. Right, right, left, and right. Okay. The enantiomer, how do you do the enantiomer? You give yourself the finger from your left hand. Like this. So you have this D-glucose. Does it fit the definition for a carbohydrate? Polyhydroxyl, ketone, or aldehyde. That's why we're doing carbohydrates right now. Because you've learned all of these reactions with alcohols. You learn all of these reactions with ketones and aldehydes. The main reaction that you'll need to know for carbohydrates, though, is that it doesn't look like this in your body. Because when you digest glucose, you're in a very acidic, aqueous environment. Let's not put aqueous. Let's put acidic, though. Super acidic. Oh, that's not it. What's in your stomach? Your stomach has gastric acid. That's not sulfuric acid. Gastric acid is HCl. Did you know you had HCl in your gut? So there's going to be some acid catalysis to make what? Well, what's the main reaction that we were focusing on today? Acetals and hemiacetal. If you think about these reactions, you have to get to the hemiacetal before you get to the acetal. Okay, so this comes first. We are going to do a hemiacetal reaction on this aldehyde. How do you get hemiacetals? It's a carbonyl group plus an alcohol, ROH. Holy smokes. We have a carbonyl, and we have so many alcohols, so many hydroxyl groups. The beauty about glucose is that it cyclizes to a very stable six-membered ring that's in a chair conformation. It's pretty remarkable that nature chose glucose as the main carbohydrate because you could form this very, very stable six-membered ring. So where's that six-membered ring? I know there's a lot of notes here. If you have this carbonyl group, you can even make it an aldehyde, and you add your alcohol. Remember what that hemiacetal looks like? The hemiacetal has an OH and your alcohol that attacked. What am I doing here? I'm a little nervous about doing a hemiacetal reaction on this molecule. So I'm going to refer back to a very, 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 very simple example. And I noticed that, that oxygen is connected to this dot in the hemiacetal, and the carbonyl oxygen became a hydroxyl group. This is the dot right here. Okay, not the best way to do that, but that's the carbon that's being attacked. If I told you that it's a six-membered ring, 1, 2, 3, 4, 5, it's this oxygen right here. That oxygen is doing the attacking. When you see the video and when you have some practice, this is going to be very, very easy. And I'm going to show you shortcuts, right? I'm not showing you really shortcuts here. I'm just trying to give you a flavor of what molecules you'll be working with. The six-membered ring looks like this. That O is part of the six-membered ring. There. It's this. Wait, give me 1 second. Get rid of this hydrogen. So you still, that oxygen still has 2 lone pairs. How can I help you out here? I can help you out by putting the dot. So the dot's right here. That dot. How else can we help each other out? 1, 2, 3, 4, 5, 6. 1. I want to make sure I don't put a number where I need to draw something. 1, 2, 3, 4, 5. 6 is hanging off the ring. Great. 6 is here. Okay. I'm not telling you what direction to draw the OH. The OH on 2, the OH on 3, the OH on 4, not the OH on 5, because look, the OH on 5 was the attacker. Look on your simple example. The attacker doesn't have the H anymore. So I'm hoping that people are very, or at least close to being very familiar with your Unit 2 now, Hemiacetal. What happened to this oxygen here? The carbonyl oxygen became an OH group. So arbitrarily, I'm going to put the OH pointing up. Again, I know there's a lot of notation, but this happens all the time in your body, and a lot of things are happening at the same time. That O, why don't we label it? Let's put a little star. Okay. Because that oxygen is this one right here. This oxygen with the pink dots, the pink lone pairs, is the one that attacked. What haven't we taken account for? We haven't done the OHs that are in the middle. Don't worry about how I'm going to draw the OHs. I'm going to draw this OH down, OH up, OH down. It's a lot. What did I start with in terms of this conversation? I started with the idea that carbohydrates are alcohols and aldehydes and ketones in the same molecule, that it can make a hemiacetal. Where's your hemiacetal in this molecule now? You see it's right here. In the video, I'm going to take this a little more stepwise, okay? I know that we're not familiar with these types of drawings where we have horizontal lines. There's a reason why people do this. Okay? There's a reason why I drew the OHs in this pattern, okay, that I haven't explained just yet. That will all be in the video. But do you see why this is pretty stable? These chiral carbons are set. The 2, 3, and 4, and even the 5, they're set. They don't change when you do a hemiacetal formation. The OHs on 2, 3, and 4 are always going to be like this. Look what's happening. Up, down, up, down, up. I betcha if you drew this as a chair conformation, you could get a chair conformation that has equatorial up, equatorial down, equatorial up, equatorial down. Now I don't have equatorial and axial. This is a different kind of drawing. This is called a Haworth projection. For a Haworth projection, you don't have equatorial axial. Everything looks straight up or straight down. But in real life, when you put it into a chair conformation, yes, you can get all of these groups to be equatorial. Equatorial because equatorial locations are very stable. You don't have bumping between an axial group and the hydrogens that are axial. Okay, so that's, again, you have to recall a little bit of Organic Chemistry 1 to be successful in Orgo 2. The first two videos will cover this. So yes, there will be about an hour of videos that sort of expand upon all of this. So again, if you're not catching this, okay, make sure you review your Unit 2, especially the Hemiacetal part of it. But the first two videos in Unit 3 will talk about this. The last video, the third video in Unit 3, most likely will connect these two molecules, or connect two carbohydrate molecules to make what's called a disaccharide. Right? So definitions are going to be kind of, there's a lot of definitions, but we'll get through that as well in the videos. All right. Are there any questions, either from the class or from Jose? If you look at the Moodle, look on Moodle. Again, don't forget our office hours, Jose's and mine. Why don't I say we're gonna end a little bit early, okay? And I'll get started on those videos. But why don't everyone take a picture of your notes for 2 extra credit points? Not all of your notes. I want to make sure that I want to make sure that people are at least getting introduced to the carbohydrates. So the notes that I want you to take a picture of and to email Jose. Don't email me. Email Jose these notes right here. Because this is my attempt to connect all 3 units together. Okay. I'll keep this up for a little bit, maybe for 5 to 10 minutes if you want to recopy it or copy it. If you're done and you want to go ahead and email Jose, go ahead and do that, and you can leave the room. You don't have to stay in the room. You could leave the room, then email Jose if you want. Okay. Let me see how many people are here, and then Jose and I can chat. Oh shit, Jose, how much extra credit did I say this was? Okay. Oh man, how many people are coming to? How many people came to office hours yesterday? Are they getting it or slowly getting it? Okay. No, they're having trouble with that. Epoxides. So there's at least a couple of people who know how to do that. Okay. Um, See, I didn't teach your class, Haworth, when you took it. No, I didn't. No. I didn't. I didn't tell you why you need to draw the OH going down and this OH going up. No, 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 no. Yeah, you're mixing. You're confused. You're talking about this carbon that's pink. I'm talking about all the other carbons. No, that you're still confusing things. This is R and S. So when you have something that's R, it has to stay R in the cyclic version. But you don't. I didn't teach you how to convert this into this. No, I didn't. Yeah, I did it. Oh, I'm still recording. Shoot.